Imagine the night sky ablaze with a light brighter than any star. This isn't science fiction, it's a supernova, a cosmic event of incredible power and beauty. Supernovae are the explosive deaths of stars, marking the end of their life cycles in a blaze of glory. These events are so bright they can outshine entire galaxies for a short time. They are visible across vast distances, attracting the attention of astronomers and stargazers alike. To understand supernovae, we must understand the life cycle of stars. Stars are born from collapsing clouds of gas and dust. Gravity pulls these materials together, increasing density and temperature at the core. Eventually, the core becomes hot and dense enough to ignite nuclear fusion, the process that powers stars. Throughout their lives, stars maintain a delicate balance between the inward pull of gravity and the outward pressure from nuclear fusion. This balance determines their size, temperature, and lifespan. Massive stars burn brighter and hotter but have much shorter lives than smaller stars like our Sun. Our Sun, a relatively small star, will live for billions of years. While supernovae mark the end of a star's life, they also represent a beginning. These events are essential for enriching the universe with heavy elements and triggering the formation of new stars and planetary systems. The intense energy released during a supernova explosion creates elements heavier than iron, elements that cannot be formed through the normal fusion processes within stars. These heavy elements, including gold, silver, and uranium, are dispersed into interstellar space by the supernova's shockwave. This material, enriched with the building blocks of planets and life, eventually becomes part of new stars and planetary systems. The atoms that make up our bodies, the Earth, and everything around us were once forged in the fiery hearts of stars and scattered across the cosmos by supernovae. Supernovae, the awe-inspiring explosions that mark the end of a star's life, are not a one-size-fits-all phenomenon. Astronomers eager to decipher the secrets held within these cosmic blasts have developed a classification system to categorize these stellar explosions. This system helps us understand the different pathways that lead to a star's explosive demise and the unique characteristics of each type of supernova. The primary classification of supernova divides them into two main types, Type 1 and Type 2. This distinction is based on the presence or absence of hydrogen lines in their spectra, which provides clues about the composition of the exploding star and the processes that led to its demise. Type 1 supernovae lack hydrogen lines in their spectra, suggesting they originate from stars that have already shed their outer hydrogen layers. Type 2 supernovae, on the other hand, exhibit prominent hydrogen lines, indicating they arise from stars that still possess their outer hydrogen envelopes. This fundamental difference in their spectra points to distinct evolutionary paths and explosion mechanisms for each type of supernova. Within each main type, further sub-classifications exist based on more subtle spectral features and light curve characteristics. These subcategories provide astronomers with a more refined understanding of the specific conditions and processes involved in each supernova event. By carefully analyzing the light emitted from these distant explosions, astronomers can piece together the intricate stories of stellar death and the profound impact these events have on the cosmos. Type 1 supernovae, characterized by the absence of hydrogen lines in their spectra, arise from a specific type of stellar remnant known as a white dwarf. White dwarfs are the incredibly dense Earth-sized remnants of low-mass stars like our Sun. These stellar embers have exhausted their nuclear fuel and are no longer capable of generating energy through fusion. Despite their quiescent nature, white dwarfs can still meet a dramatic end under certain circumstances. Type Ia supernovae, the most common subtype of Type 1, occur in binary star systems where a white dwarf orbits a companion star. The white dwarf's intense gravity can pull material, primarily hydrogen and helium, from its companion, gradually increasing its own mass. As the white dwarf accretes more and more material, its internal pressure and temperature rise. Eventually, the white dwarf reaches a critical mass known as the Chandrasekhar limit, equivalent to about 1.4 times the mass of our Sun. At this point, the internal pressure can no longer support the weight of the star, and a runaway nuclear fusion reaction ignites, consuming the white dwarf in a thermonuclear explosion. The resulting explosion is incredibly luminous, briefly outshining entire galaxies. The white dwarf is completely obliterated, leaving behind no remnant except for a rapidly expanding cloud of debris enriched with heavy elements. Type Ia supernovae are particularly valuable to astronomers because they have very consistent peak luminosities, making them excellent standard candles for measuring cosmic distances. Unlike their Type 1 counterparts, Type 2 supernovae originate from the demise of massive stars, those with at least 8 times the mass of our Sun. These stellar giants live fast and die young, exhausting their nuclear fuel much more rapidly than their lower mass brethren. As they age, these massive stars fuse progressively heavier elements in their cores, building up layers like an onion, with the heaviest element, iron, at the very center. The formation of an iron core marks a turning point in the life of a massive star. Iron fusion does not release energy like the fusion of lighter elements. Instead, it consumes energy, robbing the core of the outward pressure needed to support the star's immense weight. The core, no longer able to withstand the crushing force of gravity, collapses in on itself in a fraction of a second, triggering a shock wave that rips through the star's outer layers. This core collapse is a cataclysmic event, releasing an unimaginable amount of energy in the form of neutrinos and electromagnetic radiation. The shock wave, powered by this energy, violently expels the star's outer layers into space, creating a supernova remnant, a vast, expanding cloud of gas and dust enriched with heavy elements synthesized during the star's life and death. The core itself, depending on its mass, collapses into either a neutron star, an incredibly dense ball of neutrons about the size of a city, or a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Type 2 supernovae, with their dependence on the complex processes of massive star evolution, exhibit a wider range of luminosities and spectral characteristics compared to their Type 1 counterparts. The classification of supernovae extends beyond the basic distinction between Type 1 and Type 2. Astronomers have identified several subtypes within each category based on subtle differences in their spectra and light curves, the graphs that depict the evolution of their brightness over time. These subtypes provide valuable clues about the specific mechanisms and progenitor stars involved in each supernova event. For instance, Type Ib and Ic supernovae, while lacking hydrogen lines like their Type Iaa relatives, also exhibit a lack of helium lines or weak silicon lines, respectively. These spectral differences suggest that these supernovae arise from stars that have lost their outer hydrogen and helium layers, possibly through strong stellar winds or interactions with a binary companion. Type 2 supernovae also exhibit a variety of subtypes based on the shape of their light curves. Type 2p supernovae display a plateau in their light curves where their brightness remains relatively constant for a period of time after the initial explosion. This plateau is thought to be caused by the expansion of the supernova shockwave through the star's dense outer layers. Type 2L supernovae, on the other hand, show a linear decline in their light curves after the initial peak. These variations in light curve shapes provide insights into the progenitor star's mass loss history and the structure of its outer layers. By studying these subtle differences between supernova subtypes, astronomers continue to refine their understanding of the diverse pathways that lead to these spectacular cosmic explosions. The tipping point, setting the stage for stellar explosion. Deep within a star, a delicate dance between gravity and nuclear fusion occurs. Gravity pulls inward, while nuclear fusion pushes outward. This balance allows the star to shine for millions of years, but as the star ages, it consumes its nuclear fuel. This sets the stage for its dramatic demise. For massive stars, the core becomes iron, leading to a supernova. The core collapses, resulting in a cataclysmic explosion. Core collapse. the heart of a Type II supernova. The core collapse of a massive star is one of the most violent events in the universe, unleashing unimaginable energy in seconds. As the iron core collapses, its density skyrockets, forming neutrons. Neutronization releases neutrinos, carrying away collapse energy. A shockwave forms, propagating outward at nearly the speed of light. This shockwave can rip the star apart. The shockwave loses energy, stalling out. Neutrinos revive the shockwave, allowing it to continue outward. This neutrino-driven mechanism is essential for a successful supernova explosion. The shockwave, a tsunami of energy through stellar layers. Re-energized by the neutrino wind, the shockwave surges outward, unleashing a tsunami of energy. It heats and compresses the material, triggering nuclear reactions and forging heavy elements. The shockwave reshapes the material, creating intricate filaments of gas and dust. It accelerates particles, generating cosmic rays that influence galaxy evolution. The shockwave expels material, creating the supernova's brilliant display. Supernova remnants glow brightly, marking the grave sites of once mighty stars. Section 4. Thermonuclear runaway, the white dwarf's explosive end. While core collapse supernovae mark the explosive deaths of massive stars, white dwarfs, the stellar embers of stars like our Sun, can also meet a fiery end through a different but equally dramatic process. Thermonuclear runaway. In binary star systems where a white dwarf orbits a companion star, the white dwarf's intense gravity can siphon off material from its companion, gradually increasing its own mass through accretion. As the white dwarf accretes more and more material, its internal pressure and temperature rise. This increase in temperature and pressure gradually ignites carbon fusion within the white dwarf's core. However, unlike normal stars, where pressure and temperature are regulated by the star's expansion and contraction, white dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further. This difference in pressure support has dramatic consequences. As carbon fusion ignites within the white dwarf's core, the energy released does not cause the star to expand and cool as it would in a normal star. Instead, the energy release increases the temperature further, accelerating the rate of nuclear fusion. This positive feedback loop, known as thermonuclear runaway, quickly escalates, consuming the white dwarf in a matter of seconds. The energy released during this runaway fusion reaction is immense, completely obliterating the white dwarf and leaving behind no remnant except for a rapidly expanding cloud of debris enriched with heavy elements. The resulting explosion, known as a Type Ia supernova, is incredibly luminous, briefly outshining entire galaxies. These explosions, with their consistent peak luminosities, are valuable tools for astronomers, serving as standard candles for measuring cosmic distances and probing the mysteries of the universe's expansion. Section 5. Supernova remnants, echoes of a star's demise. Long after a supernova fades, its remnants linger for millennia. These structures illuminate stellar death and enrich the interstellar medium. They glow brightly at multiple wavelengths, from radio waves to X-rays. The shockwave heats and compresses gas and dust, creating intricate filaments and knots. These structures provide insights into supernova dynamics and the interstellar medium. Supernova remnants are dynamic environments shaped by ongoing interactions. They sweep up interstellar gas and dust, enriching it with heavy elements. This enriched material seeds future stars and planets, building blocks of life. Studying these remnants reveals the history of cataclysmic events, echoes of a star's demise. They offer a window into the universe's evolution. From core collapse to cosmic afterglow. The life cycle of a star is a delicate balancing act between gravity and nuclear fusion. As a star ages and exhausts its fuel, gravity gains the upper hand. For massive stars, this leads to a spectacular supernova explosion. The core collapses inward, unleashing tremendous energy. A shockwave propagates outward, potentially ripping the star apart. Stellar remnants, neutron stars, black holes, and magnetars. A supernova explosion leaves behind a profoundly altered cosmic landscape. The once bright star, having exhausted its nuclear fuel, is reduced to a dense, compact remnant. The remnant's nature depends on the progenitor star's mass and the supernova details. Neutron stars are incredibly dense balls of neutrons about the size of a city. They exhibit phenomena like pulsars and magnetars with powerful magnetic fields. More massive stars form black holes, regions where gravity is so strong that nothing can escape. Rarely, a core collapse produces a magnetar, a neutron star with an exceptionally strong magnetic field. Section 3. Cosmic alchemy, the creation and dissemination of elements. Supernova mark the end of a star's life and create elements heavier than iron. These elements, essential for life, are forged in supernova shockwaves. The shockwave disperses these elements throughout the galaxy. This enriched material forms new stars, planets, and life itself. Building blocks of the universe. Supernovae play a pivotal role in element formation and distribution. Elements heavier than iron, like gold and uranium, are synthesized in supernova explosions. This process, nucleosynthesis, creates the rich variety of elements in the cosmos. These elements are ejected into space, enriching the interstellar medium. This material forms new star systems, contributing to planets and life. The calcium in our bones and the iron in our blood were forged in dying stars. Supernovae are crucial in the grand tapestry of universal evolution. Section 2. Stellar and galactic evolution, cosmic shapers. Supernovae are fundamental agents of change, influencing the evolution of stars and galaxies. The energy released can trigger new star formation, reshaping galaxies. Shockwaves compress gas clouds, triggering star formation. This leads to new stars in previously inactive regions. Supernovae populate galaxies with new star generations. Their impact extends to entire galaxies. Ejected material alters gas and dust distribution, influencing galaxy structure. Supernovae drive winds that affect star formation rates. Remnants like neutron stars and black holes play significant roles. They influence surroundings through gravitational interactions and radiation. These objects add complexity to galactic environments. Supernovae are key players in stellar and galactic evolution. They shape star life cycles and galaxy structures. Without them, the universe would be much quieter. Section 3. Cosmic rays and neutrino emission messengers from explosions. Supernovae are prolific sources of cosmic rays and neutrinos. Cosmic rays are high-energy particles traveling at nearly the speed of light. Neutrinos are almost massless particles that interact weakly with matter. They escape supernovae almost unimpeded, revealing star core processes. Neutrino observatories capture these elusive particles. Studying them helps us understand stellar explosions and the cosmos. Section 4. Standard candles measuring the universe. One of the most profound impacts of supernovae on astronomy is their use as standard candles for measuring cosmic distances. Type Ia supernovae in particular have become invaluable tools for determining distances to faraway galaxies and probing the expansion of the universe. Type Ia supernovae occur in binary systems where a white dwarf accretes matter from a companion star until it reaches a critical mass and undergoes a thermonuclear explosion. These explosions have a remarkably consistent peak luminosity, making them excellent standard candles. By comparing the observed brightness of a type Ia supernova with its known intrinsic brightness, astronomers can calculate its distance from Earth. This method has revolutionized our understanding of the universe. By measuring the distances to galaxies hosting type Ia supernovae, astronomers have been able to map the scale of the universe and determine its rate of expansion. This has led to the discovery of dark energy, the mysterious force driving the accelerated expansion of the universe. The significance of type Ia supernovae extends beyond cosmological measurements. They provide a benchmark for calibrating other distance measurement techniques and help refine our models of galactic and cosmic evolution. By serving as reliable distance indicators, Type Ia supernovae have become cornerstones of modern astrophysics, enabling precise measurements and deepening our understanding of the universe's structure and history. In conclusion, the use of Type Ia supernovae as standard candles has had a transformative effect on astronomy. These stellar explosions have allowed us to measure the vast distances of space, uncover the mysteries of cosmic expansion, and gain insights into the fundamental forces shaping the universe. Through their study, we continue to explore the deepest questions of cosmology and our place in the cosmos. The year is 1054 AD. Chinese astronomers witness a spectacle that will forever etch itself into the annals of astronomical history. A new star, brighter than any other, blazes forth in the constellation Taurus. This celestial beacon, a supernova, is the Crab Nebula, captivating astronomers today. Located 6,500 light-years from Earth, it's a cosmic tapestry of glowing gas and dust. Its intricate filaments are the shattered remnants of the progenitor star. These filaments glow with vibrant hues representing elements forged in the supernova. At its heart lies a pulsar, a rapidly rotating neutron star. This pulsar beams out pulses of radiation, a cosmic lighthouse. The Crab Nebula stands as a celestial masterpiece, a testament to the power of supernovae. Few events have captured the imagination and ignited scientific curiosity as profoundly as supernova 1987A. On February 23, 1987, a blue supergiant star in the Large Magellanic Cloud reached the end of its life in a blaze of glory. This Type II supernova provided astronomers with an unprecedented opportunity to study a supernova in detail. One of the most intriguing aspects was the detection of neutrinos from the explosion. The remnants continue to evolve, providing insights into the long-term impact of supernova. Supernova 1987A has revolutionized our understanding of supernovae and their impact on the universe. In 1604, the last naked-eye supernova in our Milky Way captivated astronomers and sparked debate. Johannes Kepler documented this new star in Ophiuchus, its brilliance rivaling Jupiter. Known as Kepler's supernova, it left a lasting legacy on astronomy. A Type Ia supernova, it resulted from a white dwarf's thermonuclear explosion. The expanding gas and dust remnants are still studied today. Kepler's supernova remains a cosmic enigma, reminding us of the universe's vast mysteries. Supernovae, the explosive deaths of stars, are among the most awe-inspiring events in the cosmos. These celestial fireworks enrich the universe with heavy elements, trigger new stars, and shape galaxies. Their study has revolutionized our understanding of stellar evolution and the origins of elements. From nuclear fusion to core collapse, supernovae showcase extreme physics. These events create and disperse elements, forging neutron stars and black holes. Supernovae help measure cosmic distances and probe universe expansion. Once seen as omens, they now guide scientific discovery.